In this video, we are going to introduce your primary tool for solving mechanics problems involving motion and the forces that cause them. And this tool is called free body diagrams, or sometimes referred to as force diagrams, because they're a picture of the forces acting on something. We use them in conjunction with Newton's laws, particularly the second law, F equals ma, and we use them to analyze motion. So the steps here are, number one, we have to establish a coordinate system, just like we would have in all previous chapters. Next, we identify a system of interest. What mass are we interested in finding out the acceleration of? Or maybe what mass has forces acting on it, which we're interested in those forces. So we identify the system of interest. And then we sketch a very simplified picture showing only the forces that act on that object, right? Because Newton's second law says it is the sum of the external forces which act on that object that produce an acceleration, and only those. So those are the only ones we're interested in. And then we will break the forces into components as necessary. We're still dealing with motion one dimension at a time, so we need to specifically look at forces in x direction and forces in y direction, because we still want to get our acceleration in the x and acceleration in the y. And then we sum these forces in each direction separately, write the equations using Newton's second law. So we have summation of forces in the x direction is mass times acceleration in the x direction, and sum of forces in the y is equal to mass times acceleration in the y. So we write out these equations and then we solve them. Okay, so let's check out a couple examples of this. Let's say in this picture here, we're interested in finding out what is the reading in the scale, or what is the force the man exerts on the scale. So let's say force the man on the scale. This is what we're interested in finding. But by Newton's third law, we know that this is going to be equal in magnitude, yet opposite in direction, to the force the scale exerts on the man, right? So if we can find the force the scale exerts on the man, then we can just flip the direction and take the same magnitude, and then we'll have the force of the man on the scale. Right? So when we look at this, and he's in this elevator here, there's a lot of forces involved in this elevator. There's the tension, right, from the cables pulling upwards on the elevator. There is the weight of the elevator itself. There's the weight of the man. There's the force that the man exerts down on the scale. There's the force the scale exerts back up. There's I guess the weight of the scale. There's the total of all of these downward forces and normal force acting up. There's a lot of forces going on here, and if we try to analyze all of them, it's going to be a little bit overwhelming. So we go back and we think, all right, all I really needed to find was the force the scale exerts on the man. So I want to find out the forces acting on the man. So the system of interest would be what the forces are acting on, right? So I'll draw this system of interest here would be this guy, right? I'm interested in what forces act on him. And so when I just isolate him, I don't care about the tension, I don't care about the weight of the elevator, any of this stuff. The only forces I have are his weight and the force that the scale exerts back up on him. And these are the only forces. So when we make a free body diagram, we represent this man as a dot, and we have the forces acting down. There's a weight. We are on Earth, and so he has a weight here equal to his mass times acceleration of gravity, mg, and there's the force of the scale going up like this, right? We could call this a normal force as well. It's kind of up to you what you want to call your forces there, but recognize it is a normal force. And then from here, we would write out our sum of forces. The sum of forces in the x direction would clearly be pretty boring right here because there are no forces in the x direction. So sum of forces in the x direction are equal to 0. So, I mean, we can draw a conclusion from here that the acceleration in the x direction is equal to 0 as well, which he shouldn't be accelerating side to side if he's moving up and down an elevator. Then when we sum the forces in the y direction, we'll say, all right, sum of forces in the y direction will be, and here's the key part. Remember that g is not negative. G is a positive 9.8. And I use my coordinate system here. Positive y is upwards, positive x was to the right. I use my coordinate system to give my forces their sign. So I drew the force the scale exerts on the man upwards. Therefore, it is, I call the upwards direction positive, so this is a positive force. So remember, the sum is adding these up, so I have a positive force that the scale exerts, and then plus, since I'm summing, but this is a downwards arrow, so this must have been a negative, right? So plus a negative mg equals my mass times my acceleration in the y direction. Careful that we're focused on the y direction. And so I could write this then as Fs minus mg is equal to may. And then we need to be given, obviously, some other information in order to find out what this force is. But this is how we would set it up. And if we're given acceleration in the y and mass, we could find the force, right? So there we have. If we were given the acceleration, I'd like to put it off over here. Let's say if it's accelerating upwards, I would draw an arrow here and say this is my acceleration in the y direction. When I plug this acceleration in the y direction in here, it'll go in as a positive value because it was upwards. If I had an acceleration downwards, then I would have drawn an arrow, I guess I would have drawn an arrow over here downwards. So this is AY, then this would go in here as a negative value. Okay, so my arrow will translate to an algebraic sign via my coordinate system. Let's take a look at another one. Some other free body diagrams here. We have this professor pushing a cart here. We've identified two different systems. Let's say I have system 1 is both the professor and the cart and all the stuff that's in it. So we could effectively treat this entire system as just one big box. Okay? One big box here, and we don't even care what's going on within here. Right? We only care about the forces that are being applied on it outside. Right? So we have the forces being applied to our system. There's, she's in the system, pushes out. Then there's the force the floor exerts forward that acts on the system, and there's also a frictional force. And we also have a weight, right? But this would be the weight of both the professor and all the other stuff. So this is the weight of both the systems. So this W here, this is system 1. This is the weight of both the professor as well as the cart. The forward force we have is the force the floor exerts on the system. There's a frictional force acting back this way, and there's also a normal force acting up this way. If we just look at the other system, system 2, which was just the cart, then we have here's system 2. Then the external forces now, there is a frictional force back, and the professor is pushing forward this way. The weight would now just be the weight of the cart, so this is just the weight of the cart. And this force the floor exerts, well, the floor was exerting that force on the professor, and that, which is now not part of that system. So the only forward force we have is just the force of the professor. There's a frictional force, and then some other normal force, right? And these are not the same normal force. This normal force here and this normal force here are not the same. And just like these weights are not the same either. Another example, let's say that we want to find out what the tension is on this mass here. Now, tension is a pulling force, right? It's always pulling any way you look at it. So if we look at the tension in the rope, we'll be pulling down on the hand here, but it would be pulling up on the mass right here. And we also have the weight of this mass like this. But if I'm looking for the tension, I could just evaluate what is the tension acting on this mass. And so I can draw my system to be like this. This is my system of interest. I'll just draw a box around it. And I see then, let's actually do this. So here's that, and here's my mass inside here. Then the forces, this tension acts across this boundary, right? So this tension acts like that, and then the weight acts over a field, and so this acts down like that. And so our free body diagram, the only two forces we'd have would be the tension acting up and the weight acting down, and this is our free body diagram. Another note, the free body diagram, just the mass is always just a dot here, right? Regardless of how massive it is. And so the free body diagram of this guy pushing the basketball to the right is just a dot with a force to the right. And if he pushes with the same magnitude force on this car, it's still just a dot with a force to the right. Now clearly we'll have different accelerations because we'll have different masses when we write our Newton's second law, but the free body diagram looks the same. If we have multiple forces acting in the same direction, we can just add them up. So we have in this rocket thruster here, we have 4 thrusters. This rocket, we have 4 thrusters, and so we can, when we draw the free body diagram, here's the rocket, the mass of the rocket. It has some weight which acts down, obviously. There would be some frictional force we've identified. There's a normal force, the rails, the force of the rail exerting back up on the rocket, and there are 4 thrusters. So we have these all drawn here. There's this thruster, there's that thruster, all acting in the x direction. We could just as easily have drawn a free body diagram that looks like this. So we have a weight acting down here, and a frictional force like this, a normal force, and then we could have just said this is 4T, so 4 thrusters, because we'll sum up all of them in the x direction anyway. And then, like we did previously, I like to put the acceleration off over here. Here's my acceleration. It is not, I don't show it touching the mass. This is just so I know that this acceleration is caused by all of these forces together, right? So I would say here, this is acceleration in the x direction. So writing out Newton's laws, we'd have sum of forces in the x direction would be, I would have, I didn't establish a coordinate system, positive x to the right, positive y upwards. This would be 4t minus f is equal to mass times acceleration in the x direction, which then I can solve if I know, I would need to know 3 of these 4 variables there. If we have things off at an angle, then we'll need to break them into components first. So let's say that we're interested in finding the forces acting on this, or the tensions here. So maybe we're designing this and we need to know how strong of a cable we need to support this traffic light here. So we would note that there's no other masses between here and here, so the tension in this part would remain constant, as well as the tension in this part would remain constant. But these two tensions would not be the same. I can call this tension 1 and this tension 2. We have this mass in the middle, so they'll be different. So we have a whole lot of forces here. We got tension 1 pulling on the support here, tension 1 pulling up on the traffic light, tension 2 pulling up on the traffic light, and tension 2 pulling down on the rope. But I don't need to evaluate these other tensions over here. I could just identify my system of interest. All I really need, since I know those tensions are the same, up over here, and the tension will be same here and here, I can identify my system of interest as just being like this. And so then I only need to deal with these, right? So only deal with the tensions there. So then drawing the free body diagram, I have, here's my traffic light. This is the weight of the traffic light. This is tension 2, and this is tension 1. There's just these three forces here, right? T1, T2, and the weight. But in order to evaluate this, I need to sum my forces in the x direction and sum my forces in the y direction. So given the angles and the magnitudes, we can find our components. We have T2x like this, T2y, and we have T1x, T1y, and the weight, right? So then our free body diagram, although this is a sufficient free body diagram, in order to fully analyze it, we need to write it like this. And since we know that it's a traffic light, the acceleration in the x direction should be 0, the acceleration in the y direction should be equal to 0. So when we evaluate this, we have sum of forces in the x direction will be equal to, I have, using a traditional coordinate system, we have T2x minus T1x will be equal to mass times acceleration in the x direction, but this is in equilibrium, right? It's sitting there, no change in velocity, no velocity at all, and so this is equal to 0. So we would say here T2x is equal to T1x, which is what we get here. Also, sum of forces in the y direction would be equal to, we have upwards T2y, T1y, this would be T2y plus T1y, and then downwards we have a weight, so minus, all right, weight is mg, and again, this will be our mass times acceleration in the y direction. By the way, this mass is this mass here, so obviously the mass of the traffic light. And if it's in equilibrium, then this is equal to 0. The acceleration is 0, and so we would say the T2y plus T1y is equal to mg, which is what we get over here. Okay, so let's take a look at just two more here. Let's draw a free body diagram for this block of ice. We have the forces. I'll draw this to kind of sketch first. I actually like to draw my free body diagrams as more like blocks, which is okay too. The forces I have acting on it, there is a weight acting down. I have a normal force acting up. I have a frictional force acting like this, and I have some other force acting like this. By the way, it doesn't matter actually where you put these. If you wanted to put, or vector doesn't matter where it is, only the direction it's going. You could have put mg there and in here. That's perfectly fine as well. As long as you have the proper direction, that's the important thing. Our coordinate system here is a traditional coordinate system, positive x to the right, positive y upwards, and so now we have some fy which acts down, some fx like this, and so this free body diagram looks something like mg n, and actually then there's going to be an fy acting downwards, fx acting to the right, and a frictional force acting to the left. So then I can just sum them up. If I sum the forces in the y direction, we can see here, just summing these, we have sum of forces in the y direction will be normal force minus the weight minus fy equals acceleration in the y direction. Similarly with this one, we have the forces. There's going to be a weight acting down here, a normal force here, and a friction. Remember, friction always opposes motion, so that'll act to the left now, right? Because the motion is to the right. So then in this case, we see actually, so in this one, the pushing down is going to, if we have, this was mass times acceleration in the y direction. Pushing down will effectively increase the normal force, right? If we say the acceleration in the y was 0, the normal force is increased. In this case over here, by pulling up, it's going to reduce the normal force. If we say sum of forces in the y direction, this would be normal force minus the weight plus Fy equals mass times acceleration in the y direction. So you see here the normal force would be reduced. This would be our mass times acceleration in the y direction plus mg minus Fy. So by pulling up, we're reducing the normal force, and by pushing down, we're increasing the normal force. But this is how we use free body diagrams in conjunction with Newton's second law to solve problems. And so, depending on how the problem is situated, maybe we're given acceleration and we need to find forces. Maybe we're given forces and we need to find acceleration. And then maybe we can take that acceleration and we can apply the kinematic equations and talk about motion, etc. But the most important tool from this chapter is free body diagrams.